Hello students, let's go to next chapter of our syllabus, that is nothing but electrostatics. If you remember, same chapter name we have learned in 11th standard also. And if you remember, at that time already I have told you, this electrostatic is a word consists of two words. This is electro is the one word and this statics is another word. Electro correspond for electric charges or electric field. Electric field we can say, or electric charges. So this electric charges, this static means what? Fixed, they are not moved. So when electric charges are fixed, they are not moving, they are not changing their position, then whatever phenomenon comes, that phenomenon we have to learn under this chapter. That's why the name is said to be electrostatics. The charges which are static means fixed, steady, related to that phenomenons due to electric charges when they are steady or fixed. What are the phenomenons are there? That phenomenons we have to learn here. So if you remember again, apart from this, we have learned in 11th standard one law, that is nothing but a Gauss law, or that is said to be Gauss law. That is Gauss law we have learned, if you remember. So this is the Gauss law, such type of law we have learned. What exactly the Gauss law says? That total normal electric induction over any closed surface is equal to sum of the charges enclosed by that surface. Another way we can say that electric flux, there's electric flux coming out of any closed surface is equal to the total charges 1 by epsilon 0 times the total charges enclosed by that surface. 1 by epsilon 0 times the total charge enclosed by the surface. Q is a charge enclosed by that surface. Then this flux coming outward is equal to phi equal to Q divided by epsilon 0, and that is equal to integration over a closed surface E dot ds. ds is small area we have taken, and this E is electric field intensity. So this is nothing but a mathematical statement of Gauss law or the Gauss theorem sometimes said to be. This already we have learned in 11th standard. Now let's go further. In this chapter at the starting, what we have to learn? We have to learn the application of this Gauss law and what are the applications that we have to learn. So in your book in this year they have given 3 applications of Gauss law. All 3 applications today we have to complete all 3 applications. It's very simple to find out. Let's start with the first application of Gauss law, and that first application of Gauss law is nothing but what? Electric field intensity due to uniformly charged spherical shell. Electric field intensity due to uniformly charged sphere or spherical shell. Electric field intensity due to uniformly charged sphere or spherical shell, or it is said to be hollow sphere. What exactly this means? Before starting this, let us consider one sphere, and on the surface of that sphere, what we have to consider? So let us assume that, so this is a spherical surface. I will draw the smaller surface. Let us assume this is spherical surface whose radius is capital R. So this is a sphere, this is center of the sphere, and this is the radius of the sphere, that is nothing but a capital R. On the surface of this sphere we have given a steady charges. So these charges, positive charges, are accumulated on the surface of this sphere, and all these positive charges are nothing but what? They are steady, they are not moving. The charge are not moving, or we can say surface of sphere is charged with the positive charges, all these positive charges. Now apart from this, let us consider this uniform sphere of this charge sphere is kept in a medium whose this uniform charge sphere is kept in a medium, a charged hollow sphere or solid sphere of metal placed in a medium whose permittivity is epsilon. The medium whose permittivity is epsilon, and this is equal to epsilon 0 into K. Epsilon is the permittivity of the medium where the sphere was kept. Epsilon 0 permittivity of vacuum. K is the dielectric constant of that medium. That already we know. Let us assume another condition here. Let us consider sigma is a charge density. Charge density means charge per unit surface area. So sigma is the charge density. Charge divided by surface area. So area of the sphere, charge divided by area of the sphere. From this find out the charge. So this is equal to Q divided by area. Find out the Q. So this implies that Q equal to what? Q equal to what? This comes here, sigma into area of the sphere. Sigma into area of the sphere is 4 pi r square. So that is the value of q equal to sigma into 4 pi r square. That value we get here. Okay, is that clear? After that, we know according to Gauss law, what it says, the total charge enclosed by any closed surface is equal to what? It is q equal to what? Sorry, total charge enclosed, that is total charge enclosed, not charge, electric flux coming from the closed surface equal to what? Charge divided by epsilon 0. Suppose this is equation 1. Charge divided by charge divided by epsilon 0, and for air or vacuum the epsilon equal to 1. So that we have just written on this equation. Now another form, the what we have to do, so to find out, suppose I want to find out here the total charge. I want to find out total charge at a distance. Suppose from the center we have taken one point P here somewhere at a distance of small r. So this small r would be this point P. I want to find out electric field at this point P. Okay, outside the charge conducting sphere. What should we do? We have to draw the concentric sphere whose radius is r, and point P would be on the surface of this sphere. So let us draw this concentric sphere. So I will draw it by dotted line, and this concentric sphere is said to be, this concentric sphere, just I have drawn it here by dotted line. That concentric sphere is called to be, it is said to be the Gaussian surface. That surface is said to be Gaussian surface or Gaussian sphere. Imaginary sphere we have drawn by dotted line, that is said to be Gaussian sphere. Now here, as let us consider within this, the point P is somewhere here. Let us consider here a small area on which the point P would be, and that area is ds. Let us consider the small area on this area ds. Now this point P would be here. So let us draw here the perpendicular, that is, it shows the electric field vector E. Electric field vector E, and this area ds, draw perpendicular to area ds. This is perpendicular to area ds, and this is electric field vector. Both of them are coming outward and perpendicular to the surface ds. So if they are parallel, what should be the angle? Angle between ds and E, that angle theta equal to 0. If theta equal to 0, cos theta means cos 0 equal to 1. So that comes to be 1. Then we can find out according to Gauss law, this left hand side we have, right hand side we have written. Left hand side is what? E dot ds, dot product is there. Whenever dot product is there, there must be sine or cos theta. So here it should be cos of theta. But theta is 0. So what it is? E into ds. That would be the left hand side according to Gauss law. Just this is nothing but for area ds. This should be the value. But I want to, for whole sphere we want to find out the value. So what should we do? We should do, how can we find out phi? So that phi can be find out by just integrating this equation. So we can write this is equal to phi. Okay, so just this is equal to phi. Just find out the, so phi equal to integration of E into ds across a closed surface. Now here E is a constant, take it outside the integration over a closed surface, into it is ds. So this ds is a very small area. If we take integration, we get a whole circumference or a whole sphere we have to consider, whole Gaussian surface we have to consider, and that is nothing but the area of this dotted sphere, and that comes to be equal to E into 4 pi r square, and this r would be small r square. So that phi equal to, let us consider this is equation 2. So if you consider equation 1 and 2, left hand side is same, so right hand side must be same. So to find out the right hand side of both equations 1 and 2 are must be same, because left hand side is same, that is nothing but a phi. So we should equate equation 1 and 2. If we equate equation 1 and 2, what we can write here? We can write this as E into 4 pi r square from equation 1 to E into 4 pi r square equal to Q divided by epsilon 0. Our aim is to find out this E. So this implies that E equal to Q divided by 4 pi epsilon 0 into r square. and this will give the electric field intensity at a point P at a distance small r from the charge conducting sphere, and that we have find out the equation for electric field intensity, that is nothing but q divided by 4 pi epsilon 0 into r square. Now question comes here, if you remember this we have find out what is q. Q equal to sigma into 4 pi r square. Put this value here, so you can write this as equal to sigma into 4 pi r square divided by 4 pi epsilon 0 r square. 4 pi cancelled out. Okay, 4 pi cancelled out. What is remaining? Remaining thing is sigma into r square divided by epsilon 0 into small r square. That is electric field intensity. We have find out another form of equation for electric field intensity. So this is the electric field intensity at a distance r outside the charge conducting sphere, that we have find out by these two equations. There is the first one, there is second one. Same thing they have shown in your book. Equation 8.3 is this, and equation 8.4 is this. Now there are cases, two cases we have to consider. Let's start with the case first. So let's start with the case first. What is the first case? First case says that if we reduce the surface, if we reduce the distance, not surface, this r is reduced, so that point P reach on the surface of the sphere, what would be the equation for electric field intensity? So that we have to find out. As point P move to the surface of conducting sphere, so here capital R equal to small r. Okay, if we put it here, capital R equal to small r, E comes to be what? E comes to be, according to this, Q divided by 4 pi epsilon 0 into capital R square. Or according to this, both are same, so they get cancelled out. This comes to be sigma divided by epsilon 0. So this is the first case when point P is shifted to surface of charge conducting sphere. This would be the equation for electric field intensity. Let's go to case second. So this case second says that when we shift the point P, when we shift this point P from this at a distance r, not on the surface, if it is inside the sphere, conducting sphere, as it is conducting sphere, inside the conducting sphere, electric field intensity would be 0. So this would be the second case as they have discussed, because inside the charge conducting sphere, charge density is 0, sigma is 0, and sigma equal to 0 means E equal to 0 inside the charge conducting sphere. So this is the first application of this, that is Gauss law we have learned to find out electric field intensity outside charge conducting sphere, and that we have find it out. So this, in this fashion, we have completed the first application of the Gauss theorem or Gauss law. Now let's go to the second application of Gauss law. What is the second application of Gauss law that we have to learn? So here just we have applied for sphere. Similarly, we can apply the same Gauss law to the cylinder or the length of the wire. Long, infinitely long wire or cylinder is there. In that case, we can apply it also. So let us consider here the sphere. Let us consider this as a cylinder. Let us consider this as a cylinder. What should be the application? Electric field intensity due to infinitely long straight charge wire. Electric field intensity due to infinitely long charge straight wire or cylinder. So let us see here, electric field intensity due to infinitely long charge the straight line wire or cylinder, that we have to consider. So let us consider this is cylinder, and this cylinder is charge one, whose radius we have to draw here. This radius of the cylinder is suppose capital R is a radius, and as it is charged, so suppose positive charge is given to the outer surface of the cylinder, or we can say charge straight line wire this is. So we have given this as a positive charge to this cylinder or wire. So it is a straight line cylinder or wire which is charged. Now let us consider similar to initial one, it is sphere, it is cylinder only, that is the difference. Let us consider at a point P at a distance small r from the axis of cylinder or axis of wire where we want to find out electric field intensity. So what should we do? We have to draw the imaginary cylinder with point P on the surface of that cylinder. So let us draw this dotted line, Gaussian surface or Gaussian cylinder we have to draw. So I have drawn this by dotted line such that this point P comes on the surface of this Gaussian cylinder or Gaussian wire, we can say. Now here let us consider, initially if you remember we have seen the sigma, surface charge per unit area. Here we have to consider the linear charge density lambda. Linear charge density lambda, charge per unit length, that is said to be linear charge density. It is Q by L. It is said to be Q by L. So this equation implies that Q equal to lambda into L. So this equation we have to use later on, because charge density we have find out. From that we have find out the charge, lambda into L. Charge density, linear charge density into length of cylinder. Now here, suppose such type of charge conducting wire, straight line wire or cylinder infinitely long, it is kept in a medium whose what permittivity is epsilon. So we can write epsilon equal to epsilon 0 k. It is similar to initial case. Epsilon is a permittivity of medium where we have kept this wire. Epsilon 0 permittivity of vacuum. K is nothing but dielectric constant. So here again, according to Gauss law or Gauss theorem, we have to use the same thing to find it out, so that it is application, second application of Gauss law. So we are going to use the Gauss law to find out electric field intensity. Now how can we find out? So as we know, again draw, just take a small area ds such that this point P comes on this area ds. Draw the electric field vector and another line perpendicular to area ds. Again here theta is 0. If theta is 0, cos 0 is what? Or cos theta equal to 1. Okay, then you can write again same equation, E dot ds, the phi equal to E dot ds equal to E into ds into cos theta, but cos theta is 1, it is nothing but what? E into ds. But what? This is for only this small portion, but we have to take a whole Gaussian surface, so we should take integration. So we can write this as integration over a closed Gaussian surface E into ds. E is constant, take it outside, just integration over a closed surface of ds. ds is now what? The area of this Gaussian sphere, not a sphere, it is what? Cylinder. What is the area of cylinder? It is 2 pi RL. So we can write this phi equal to E into 2 pi R into L. Equation 1 suppose. Okay, but according to Gauss law, what is phi? Phi equal to Q divided by epsilon 0. It is equation 2. Equate equation 1 and 2 similar to initial case. Left hand side is phi, right hand side must be same. So we can write here the equation as E into 2 pi R into L equal to Q divided by epsilon 0. Put the value of Q. So we can write this as lambda into L divided by epsilon 0 equal to E into 2 pi RL as it is. L from left side, L from right side cancelled out. Find out E. So E equal to lambda divided by 2 pi epsilon 0 into R. So we get this as an equation for electric field intensity at a distance small r away from a charge conducting straight wire or charge conducting straight cylinder of infinitely long length. So we get this equation as nothing but equation 8.6 from your book. Now point to remember here, if the sphere is like this, it is positive charge, E comes out, E electric field vector comes out, but the sphere is such that such type of sphere is there having suppose the charge where negative ends on the cylinder, the direction of electric field is inside like this. In this case it is outside. Electric line of forces move from positive to negative, so it is moving away. Start from positive, ends on negative, so it goes inside if the negative charge is given, comes outside if the positive charge is given. That was shown in diagram 8.3 in your book. So these are the two applications of this Gauss law. Let's go to the third and last application of Gauss law, and that is to the plane sheet. If we have charge conducting plane sheet, how can we use a Gauss law or Gauss theorem? That we have to consider. So third application is nothing but electric field due to charge infinite plane sheet. Electric field due to charge conducting infinite sheet. Infinite sheet means what? It is infinite sheet we have to consider. So such type of sheet we have to consider. This is an infinite sheet. Suppose infinite, it goes out there and here, and having it is charge 1. Charge 1 means what? It is charge given to the surface of the sheet is what? Positive charge is given. Now let us consider the cylindrical part that is passing from this. Suppose such type of cylindrical part we have considered to this side, and it comes from this side also. Same cylindrical part come from this side also. So these are the 2 point P and P dash. So P and P dash are the 2 points. Let us consider this as an area. This is the area ds. Then this is again the area ds, because both are the same cylinder coming from both sides. So this area ds and ds. The total area, this would be capital A, this would be capital A. Now again here we have to draw the electric field intensity perpendicular to this area ds and the perpendicular to ds to right hand side, as well as you can write here to the left hand side E, and this is for ds component. So we get such type of diagram. Now here let us consider some point here P. This is point P kept at a distance away from this as a R, kept at a distance of R from the sheet, or from the sheet we have kept this point P at distance R. Then we have drawn this as a Gaussian cylinder around the point P. Now here contribution of electric field due to this curved cylindrical part is 0. So only the part remaining is ds to right hand side and ds to left hand side. That will contribute to electric field intensity. Now here we can write according to Gauss theorem again. So we can write here phi equal to what? Integration over a closed surface E dot ds. E dot ds I am saying, and that is due to what? That is due to the point to right hand side, that is nothing but a P, plus integration of closed surface E dot ds, and this is due to the point P dash. Both sides we have to consider here, P and P dash. As theta equal to 0 again, that they are parallel, theta equal to 0, this implies that cos theta equal to 1. Okay, so we can write this as equal to, we can write this as equal to, again here E is common, it is constant, integration over surface of ds plus E is again common, integration over closed surface of ds, cos theta is 1. Just we have used the formula for dot product. Finally, this is nothing but A. This side it is total area is A. This side it is total area is A. So it comes to be E into A plus E into A. So it comes to be twice E into A. That is phi equal to equation 1. Suppose twice E into A, phi equal to. But according to Gauss theorem, what is phi? Phi equal to Q divided by epsilon 0. Phi equal to Q divided by epsilon 0. That is nothing but according to Gauss theorem. Let us consider here surface charge density. Surface charge density sigma equal to charge divided by area. This implies that charge equal to sigma into area A. Sigma into area A. Now just equate equation 1 and 2. Suppose this equation 2, as left hand sides are same, right hand sides merge with same. Equate the equation. So we can write here the 2EA equal to Q divided by epsilon 0. Put the value of Q from this equation. So we can write this as sigma A divided by epsilon 0. So here it is 2EA. Area from left side, area from right side cancelled out. So E equal to sigma divided by twice epsilon 0. So this is the equation for electric field intensity. Electric field intensity due to charge conducting infinite sheet, it comes to be sigma divided by twice epsilon 0. So these are nothing but what? The three application of Gauss law that we have learned up till now. The next period will start with an electric potential and potential energy. In next period we'll start this. Thank you, take care, and try to read try to watch my video first, then just try to read the same topic from your book. Definitely you get a better understanding of the topic. Thank you.